All right, we're the spark plug team. For those of you that might not know, this is a spark plug. It's a small device that you can find in any gasoline-powered car. Its sole purpose is to emit a bolt of electricity that ignites the fuel and makes sure that gets your vehicle up and running and keeps it running. So on a round-trip drive to Boston and back here to Olin, this generates about 450,000 sparks and a cumulative total of 1.5 billion volts of electricity. So once your spark plugs become worn out or dirty, they stop producing strong enough spark to ignite the fuel and air mixture, and they need to be replaced. So I'll pass this around. This will not shock you as well.
These are the tips that we'll be talking about later if you are interested in. You don't have to really sort of look closely.
They're really tiny.
The other thing you'll notice is that we're all currently hooked up to a chicken fence. This chicken fence operates at 5,000 volts, really low amperage, so it's not necessarily dangerous. But your average spark plug, every time it sparks, operates at 15,000 volts. So combined, we're only going through a third of what a spark plug goes through, and it sparks about 6,000 times every minute. So this is actually like a really high stress scenario, and it's creating sort of plasma at around 107,000 degrees Fahrenheit. So there is a lot of high stress, which is why we have some interesting materials.
So we actually bought 3 different types of spark plugs. We bought a platinum one and then 2 iridiums. One is a double iridium. Actually, all of them came out of John's car. So essentially, we decided to kind of take apart, because most of the differences in the spark plugs are at the tip, where actually the plasma happens and it like sparks the fuel. So we decided to see like kind of what else is in the spark plug and like do some etching on the other materials there as well. So actually the spark comes in through this iron part, it goes through this graphite part, then goes into this nickel and copper area that kind of like leads into the platinum or iridium, and then creates the spark. We actually found that in the iron parts they were rolled, and as you can see up close, you can see the folds of the grains through the threads, and actually makes it stronger, less likely to break.
Yeah, so the next thing we were really interested in is the tips of the spark plug, which are around here. You can't even actually see it in this image. There are the little glass tubes that we're passing around. They're extremely small. So we put them into the SEM to get a closer look. The 3 tips we had were the platinum tip here, the Bosch iridium tip here, and the NGK iridium tip. Something this was sort of just to look at the macro properties. For the platinum tip, we actually noticed where we grabbed it with the pliers, it deformed a bit. Platinum is a lot softer than the iridium. And you can also see this in sort of just the, this is actually the face of the tip here. And you can see that it's a lot less, has sort of like less of a smooth finish, which we'll talk about later, but the smoother the finish, the smaller the area it has to arc across, the less current you actually need to produce the same amount of arc. So sort of the nicer finish comes with the iridium and the more expensive plugs. If you look at this first iridium plug, you can see how brittle it is. This is actually, each of these are individual grains in 3 dimensions. So it breaks right along the grains, and it's really easily seen because of how brittle it is. And then this is the most expensive plug, and we found that this had the nicest surface finish, again giving it the smallest amount of surface area, which means you have to use less current to create that arc. We can also see that there's a lot of dendrites that were formed because it's laser welded, and so it cools very quickly, and so we had these sort of tree shapes coming out in 3 dimensions, which we thought was also interesting seeing it in the SEM. And looking through our compositions, we have for the platinum, it was 87% platinum and 12% nickel. For the Bosch iridium, we had 92% iridium and 7% rhodium. And then for the NGK iridium, we had 92% iridium and again 7% rhodium. And that sort of leads into what we were doing with the alloy analysis.
So we wanted to look more into the alloys that we found in the tips. So we took our alloy phase diagrams and then we zoomed in specifically to the operating temperatures that spark plug would go through. So we looked down from 0 to 60 degrees. This would be like the ambient temperature when your car isn't operating, you would rest at this temperature. Then there's a transition temperature, and then the 500 degrees Celsius to 800 degrees Celsius is the range of like optimal operation. So while your spark plug is running and while you're driving, it can stay at those temperatures for 30 minutes to a couple hours. So this range of temperatures is what we really care about when analyzing what the alloys perform at.
Yeah, and I guess going more into detail on that. So I'm looking at the phase diagrams. So as you can see in the nickel platinum alloy, it goes into 3 phases. First being the single phase, then into the intermediate phase, and then going into the 2 phase. Then also while in the iridium rhodium, the graph actually bottoms out at 900 degrees Celsius, which means that going at the max of 800, it goes actually below this graph, which means it stays at the solids state, which is two separate compositions. They don't actually mix. And the benefits, I knew it was coming. The benefits of the iridium, I would say, is that it doesn't actually change states, which means that these don't. It will be able to last for longer because they don't have to atomically they don't change, and they can stay within one state. And so that's why the iridium is better.
And interestingly enough, the 500-800 range is described as optimal, probably not too coincidentally for the iridium tips, because they can get up to 950 degrees Celsius, and once you cross that range, you actually change into a different solid state phase for the iridium. So we hypothesized that the reason they said the optimal range is 500-800 is because past that you'd start to go through some anatomical changes as the atoms get restructured around, and it leads to increased degradation of material over time.
Yeah, and the last thing I'd also add is because they're in for the iridium, they're in 2 states. It's technically less conductive compared to copper or even the platinum. Because of its hardness properties, you're able to make the tips a lot smaller, which kind of compensates for the less conductivity, which makes it overall better product. If that makes sense.
Because the smaller volume that you have to arc across, or the smaller area that you have to arc across means that you can use less current to create that arc. So having this really hard material that you can sort of have that remains in its shape at the smaller size allows for sort of the same amount of current, if not less, to be used with more longevity if you use something that was softer but had to be a larger size. And then sort of one of the final things we looked into was the production and environmental impact. The process used to refine platinum and iridium is actually very similar to a lot of the other minerals that are the metals that were touched on, where it's sort of used some of the surface. It's mostly mined in South Africa, and it's not actually, most of the time it's not mined for directly because there's such trace quantities in the amount that you have to mine. It takes about 12 tons of material mined to produce about 1 troy ounce of platinum, which is around 33 grams. So the ratio of sort of mining and raw material that goes in to material that comes out is really quite steep, which is why it is so expensive. Iridium is about twice the price of gold per gram, and platinum is about the same. And so something we looked into is how much is actually mined every year. And for platinum, the amount that's mined per year is 46,000 pounds. And in density, if you look at the volume, it's about the same volume as one of the tables we have in the MatSci room. So that's the amount that's mined every year, and the total amount mined ever is about a quarter of the MatSci room itself. So this is something there's really low amounts of it that have ever been mined, and for iridium, it's even less. The amount mined per year is 15,000 pounds, and the amount of volume per year that equates to is about underneath one of the MatSci chairs. So the volume is really, really small for these materials, which is why they use such small amounts in the spark plugs. Interestingly, if you look at the plug, it's majority iron. And so we were looking into the embedded CO2 in that iron compared to the platinum and iridium. So for iron, there's 2.5 billion tons of iron refined a year, whereas there's only 23 tons of platinum refined every year. And so that's sort of like a huge difference in how much, but the CO2 produced per ton of iron is 1.9 tons of CO2, whereas for platinum, it's 20,000. So this is where we see the huge disparity in how much you have to mine and then refine this process. Also, it's one of those economics of scale things where there's so little being refined that it's really not the same. I dropped it. And so then the other thing that we looked into is the CO2 produced per year, because of how much iron is produced, is still much more for iron. It's about 5 billion tons of CO2, whereas it's only 500,000 tons of CO2 from the platinum. But again, that's because there's so little being used in the actual spark plug. If you look at the little tiny tips, there's 18% more, or 18 times more embedded CO2 in the tiny, tiny tips than all of the iron used in the plug. Whereas the iron weighs, about 100 times more than those tips. So the embedded CO2 for the given mass is sort of exponentially larger for the iridium, which is sort of interesting because it's just so little is used, but the impact it has just because of how rare it is and how much material it takes to refine is huge.
So in conclusion, if you're looking to buy new spark plugs, we would suggest getting the more expensive, higher quality kinds because we affirm some of these statements that the manufacturers were making, and we think that the increased lifetime is worth the proportionally increased price of buying them because then you have to worry less frequently about replacing them.
Great. Thanks.
Questions?